Okay, in this video we're going to start dealing with one of the more common intro to computer science problems, sorting algorithms. We just went over some searching algorithms, how to look for a certain value in a list of numbers. The binary search required that the list be in order. So now we're going to look at algorithms of how we could put an unsorted list in order. So you might want to sort the list 3, 1, 7, 5, 2. I trust that any of you could put that list in the right order. That's not really the question at hand here. The question is, how could we write a computer code, or how could we follow an algorithm to put this list in order, or to put any general list in order? We're going to start with the bubble sort algorithm. The bubble sort algorithm sorts a list. It compares adjacent numbers and swaps them when necessary. But we have to be a little bit careful and consistent in how we're going to go about doing this. This is a very loose description of the algorithm. Down here is the pseudocode. Again, this is a pseudocode from the textbook that we're using. It's actually really only these 3 lines of code. Very simple algorithm. What we're going to look at is how to trace it on paper. And because we're going to have so many updates of I and j here, I'll explain what these 4 statements are in a minute. We're going to use a more visual trace rather than a variable trace with I equals, j equals, and so on. You certainly could update I and j every time you run through this lines of code, through these lines of code. But there's a nice picture series we could draw that would perform the trace as well. So the bubble sort is going to take a list of real numbers n greater than or equal to 2. The algorithm, because there's subtraction involved, we have to make sure we have at least 2 items in the list. And obviously, if you only had a list of 1 item, there would be no sorting to do. There's an I and a j counter, and the command for in most programming languages, it's another control structure. It's a looping statement. But unlike the while, where the loop is conditional, right? You keep going as long as a certain condition holds. A for loop is much simpler. You're just going to count as I goes from 1 to n minus 1, counting by ones. You're going to just repeat the loop and anything inside the loop so many times. Now, this loop is indented, and usually we indent things in programming to show that this loop is inside of this outer loop. So the j loop is going to count from 1 to n minus I. I is going to go from 1 to n minus 1. So we're going to work our way through the list, and the reason we're not going from 1 to n is because once we have the first 4 numbers in the right place, or what will actually happen is the last 4 numbers in the right place, the last number is automatically going to be in place. So we don't have to sort, we don't have to make n passes through this list. We only have to make n minus 1. Okay? The way bubble sort's essentially going to work is we're going to make sure that after we go through the first time, the biggest number is all the way at the end, then the next biggest number will be in the second to last spot, and so on. Now, the second loop is going to deal with the part that's unsorted. So the first time, you're going to go from 1 to n minus I, right? N minus 1, and then you go to 1 to n minus 2 and n minus 3. So as you start fixing numbers in position here, you're never going to have to look at them again. So the second loop is going to get shorter and shorter each time. And the only real set of commands we have here is if the thing you're looking at j is greater than the next one, j plus 1, then interchange them, swap them. Now that would take some pseudocode, and you do have to be a little bit careful when you swap. You can't just say x equals y and y equals x, because then you overwrite one of the variables and lose it. But that's for another issue, and the book goes into details of how you would swap that. Again, we're just trying to follow the pseudocode on paper. So we're going to show and trace how bubble sort would sort this list. And we're going to use some little arcs to show the comparisons. And the book will distinguish between 2 types of arcs. We can use an arc with arrows on it, which means the 2 were swapped, or an arc without arrows to mean that they were just compared without swapping. Ultimately, I'm not too concerned whether you indicate whether the numbers have been swapped or not, because that'll be obvious by looking at the numbers themselves. Okay. The book also chooses to do this vertically. I tend to like to do it horizontally. I think it takes up a little bit less space, and it's a little bit more consistent with how we write things, especially if you like having lined paper. So I'm going to work on this one horizontally, but you can see the book's notation vertically, and you can ultimately choose which way you want to do it. Okay? The only issue with writing things horizontally is you'll need the commas to separate things. That's one advantage to writing it vertically. Now, the very first thing we're going to do is we're going to compare the 3 and the 1. Are they in the right order? We're trying to put this list in increasing order, so we would say no, they're not. We're going to swap them 1, 3, 7, 5, 2. Okay, then we compare the next pair, the 3 and the 7. Are they in the right order? Yes. So I don't want to put the arcs on them. Right? And then we have to keep writing this down every time, which is why we're using such a short list. We're going to compare the 7 and the 5. They are not in order, so they need to be swapped. So then we will get 1, 3, 5, 7, 2. And then we will compare 7 and 2. They are again out of order, so we will have to swap them. And after the first pass through the list, we now know that the number 7 is in the right spot. So we can put a little box around it to indicate that the 7 is in the right spot. It's not going to ever have to move again, so we'll never have to compare to it again. And that's why this second loop, as I gets bigger, the J loop gets shorter, because you don't have to keep comparing to those numbers that are already in the right place. I think the reason this is called bubble sort is you've got these little arcs here. It looks like the numbers are kind of trickling or bubbling their way. You know how bubbles rise to the top? In this case, the numbers are sort of bubbling their way down to the bottom with a bunch of little swaps. Okay? So now the second time around, right, this was all for I equals 1. Right? Now we're going to go through the second time around, and again, we're going to keep in mind that the 7 is already in order. Just because we swapped a few things the first time doesn't mean that everything else is in the right order, and you can see that here, that we're not in the right order. The other thing to consider is that even if we were in the right order, the algorithm wouldn't know that until it finished. And it's not worth checking every time if you're in the right order to decide whether or not to quit. So we're going to have to continue even after we might already be in order if we're going to follow the algorithm. So again, we start at the beginning, 1 to 3. That's in the right order. So we can leave that. Okay, again, we're going to put the box around the 7. The next comparison is the 3 and the 5. Again, they're in the right order, so there's no swap necessary. And keep that box around the 7. And the next comparison is the 5 and the 2. Now they are out of order, so they are going to get swapped. And at this point, we now know that the 5 and the 7 are in order, or in the right spot. The 5 has sort of trickled its way down the list to the bottom of the remaining list. Okay? And if you notice, we had 1, 2, 3, 4 swaps. Now we have comparisons here. Now we only have 3 comparisons. The next time we'll only have 2, and then we'll only have 1. And that's ultimately how we're going to get everything to finish in the algorithm. Sorry, I was just going to move these over just a little bit here to give myself a little more room. Okay. So now we start with our 1, 3, 2, 5, 7 list. Again, the 5 and the 7 are already in the right spot, so we're not going to consider them again. We look at the 1 and the 3. They're okay, so we're not going to swap them. Next issue is to compare the 3 and the 2. They are out of order, so we are going to swap them, and we'll have 1, 2, 3, 5, 7, and now we know that the 3 is in the right spot. Now this is where, again, it's going to be tempting to stop using bubble sort. Bubble sort doesn't know that 1 and 2 are in the right spot yet, and it won't bother checking that. So if you end your trace right here, you're going to lose some points because you didn't actually perform bubble sort the way bubble sort is performed. So we have to start again and do that one last comparison, because it's always possible that these first 2 are out of order. So the next thing we do is we compare the 1 and the 2. We can see that they are in fact in the right order, and then at this point, once we decide to box this 2, we've also automatically boxed the 1 because it's the only remaining one left. Again, that's why we only have to make n minus 1 passes through. So there were 5 numbers in our list. We made 1, 2, 3, 4 passes through. Once the last 4 are in the right spot, the first one automatically is. Okay? So this would be the type of trace rather than keeping a list of I and j and updating it all the time. I think this is a much more easy to follow and sort of demonstrates what's going on with bubble sort. Takes a lot of time to do and a lot of writing, even for a list of 5 numbers. So that's probably all you would see on paper. But writing a computer code doesn't matter how big the list actually is. Okay, so it's important that you try this a few times, learn the notation, make sure you don't stop too early, and understand once you've boxed a number, it no longer gets compared. You notice we never draw an arc to any of the numbers in the boxes. And the boxes sort of help you know when you've reached the end of that next pass.